So here is the motivation. Stroke is globally #1 cause of long-term disability, #2 cause of death, 15 million cases per year. Basically, 1 in 4 adults, right, in the audience in our lifetime, we will have the chance to develop a stroke, right? So that's the potential impact. Stroke is reversible if you can treat stroke within this golden hour, a couple of hours after the occurrence of a stroke, then it's fully reversible. However, if you miss this golden hour, then time lost equal to brain loss, right? Then the standard care, right? So this is the current standard care. It's called a thrombectomy, right? The neurosurgeon will make an incision on the femoral artery on the leg of the patient, and then insert this long guide wire all the way from the leg to the brain of this patient, right, to reach the lesion of a stroke, and then to treat the stroke, right. So this is an effective method, but lots of intrinsic challenges. #1, long training time for neurosurgeons, 4 to 7 years, right? Because you may ask, right, how do I navigate, all the way from the leg to the brain? There are lots of branches of your blood vessel. The tip of this guide wire is a J shape, right? Then the neurosurgeon rotate the guide wire from outside the body. Then this J-shaped tip rotate inside the body to the desired branches to navigate to the desired branches. So it takes a very long training time to master this practice. Then these neurosurgeons, they only work in this called tertiary centers, right? Major medical centers. They are unavailable, especially in rural areas, right? For example, in Boston, we are fortunate. There are Harvard Medical School. We have this kind of centers. However, in Maine, New Hampshire, we need to transport the patient all the way from those areas to Boston for treatment. And during this transportation, the majority of the cases miss this golden hour. Right? So that's an intrinsic challenge. Cannot be solved. Then for these heroic surgeons, right, they also suffer. They suffer from accumulated radiation, right? Because they need to work under this X-ray fluoroscopy to see the exact location of the guide wire and the blood vessel to navigate it, right? For the patient, it's one time. For these neurosurgeons, it's their whole career. They suffer from this accumulated radiation from X-ray. These are intrinsic challenges, right? So my student, Kim, so he noticed this challenge, and then we propose a dramatic different idea to treat a stroke. So we call it a tightly operated, in future even autonomous robot, right? So we design a guide wire robot, right? So you can see, but the shape of this guide wire robot now is straight, not a J-shaped tip anymore. Then you may ask, then how do you navigate it? We embed this so-called hard magnetic particles, right? So imagine these are small magnets around the tip part of this soft guide wire robot. Then when you apply external magnetic field, so this is like a soft, magnet, it can bend along the applied magnetic field. Then this on-demand bending will navigate this guide wire to the desired branches of the blood vessels, right? In the brain. So that's the idea of this robot. Then it requires lots of fundamental studies, right? How much this robot, this guide wire will bend under magnetic field. We need a model. So these are fundamental mechanics, physics. We developed a quantitative model. You can see these are simulation results based on the model. These are experimental results, data. So this is very important, right? Many students want to become, especially PhD students, want to become an entrepreneur. But don't forget the fundamentals, right? Because as an MIT PhD, that's your strength. So with this, we have lots of confidence about our system. Then this model later can guide the design and the control of this robot, right? So that's #1. Then #2, now we need to design this robot, right? Because this is a guide wire. You want to apply as little magnetic field as possible to achieve the bending you want. Then the question is how to design the most agile, hard magnetic soft robot for endovascular surgery. This is a clinical problem, right? How to define most agile. So we collaborate with Dr. Aman Patel, who is the director of cerebrovascular and endovascular neurosurgery at MGH. To him, the most agile robot will reach the largest workspace. This is also actually intuitive. You want this robot under low magnetic field reach the largest possible area so that you have the highest flexibility for navigation, right? Then we convert this clinical problem into a scientific problem, right? Design problem, right? Then the problem is how to design the patterns of these small magnets inside this robot so that you can reach the largest workspace, right? So then that become a problem in my domain. So we use, based on this model, we can do thousands, even millions of simulation, right, for different random configurations. Then you can harness, right, the most advanced AI algorithm or genetic algorithm. Use that to optimize this design. Eventually, you can see this is the optimized pattern of the magnetic particles. Around the very tip, you have a high concentration of magnetic particle. In the center part, you have very low concentration because this gives the flexibility. Then around the end, you have another high concentration. So two flexibility, together, so you can reach the largest area. But with this model, we can accurately calculate what's the optimized, design to give you most agile hard magnetic soft robot. Right? So that's that. Then the third part, fabrication, manufacturing. Right? If you want to translate, you need a product level quality robot. Right? We use 3D printing. Now we have even more advanced, this fabrication process. The key idea is, so you use this direct ink writing. Then when you print this polymer ink out, you also couple electromagnet around the nozzle of the 3D printer. Then this electromagnet can reorient these magnets inside the ink you printed, so that you can program the magnetic patterns you print out. Right? So this also published in Nature, also even become the cover of Nature. Right? So we not only translate technology, we really have foundational papers, foundational, I would say fundamental science behind the technology that we translate. So then with that, it's about, implementation of the whole system, right? So we developed this full system, so fluoroscopy. We use a single robotic arm to hold a magnet, this is a magnet, to apply the external magnetic field, right? And this is a joystick controller that will control the position of this external magnet. Then we have another unit to advance or retract this guide wire robot, right? So you can see the navigation, this bending, and the advancement, retraction are decoupled. So they are not together, so that you can control them individually. So with that, let's see some preclinical results. The first one is tiny robotic aneurysm coiling, right? So this is the aneurysm in a phantom, in this phantom model, right? If you do not coil this aneurysm to protect it, it may burst. That will give the patient a hemorrhagic stroke, right? Then how to navigate these coils to this aneurysm? You can see this is under C-arm fluoroscopy. We first navigate the robot all the way to this aneurysm. Then in the second step, we will deliver the microcaster, which is a small conduit. Right? So around this guide wire robot, so then you deliver this small conduit to this the aneurysm that you want to treat. Then in the third step, you withdraw the guide wire robot. Now you deliver this platinum coil to coil up this aneurysm. Right? You can see the whole process was operated by this robotic system, and the operator, the neurosurgeon, is in another room. In the future, we even hope this is in another city, so we can remotely treat a stroke patient. Right? And also, this is VR. This is virtual environment. Right? We can visualize the whole setup in this virtual environment, and also it can make sure there is no collision between the robotic arm with the patient or with the other setting. Right? You can see very quickly you call this up. Another case is clot. This is ischemic treatment. Right? So with a similar process, you deliver the guided wire robot, and with this is a stent retriever. Right? It's like a fishnet, capture this clot, and then you retrieve the clot together with the robot back to the body. Then you clear this stroke. Right? So not only that, because we are targeted at a translation, we want to make this technology as mature as possible. We tested this in pig models, porcine models. So this is the pig forearm. So in this this flexed position, this is a mature protocol to simulate the blood vessels, arteries inside the human body. Now use this model. So we do the navigation. You can see this pig is covered by this white sheet. You cannot see it visually. You only can see the blood vessels, the guided wire robot through X-ray fluoroscopy. And here is the robotic arm with the magnets. You can see. Then by positioning this magnet to desired locations, you can remotely guide the navigation of this guided wire robot to desired branches. This is quite a challenging navigation, even for manual operation. But with this robotic system, we can quickly navigate this guided wire to desired location. And probably you cannot hear this beeping sound. I'm hearing this beeping sound, which is the heart beeping of this pig model. So it's still alive during the whole operation process. Then let's compare with standard care. Compare with manual operation. Number one, impressive comparison is this. As I told you, for those manual operations, it takes over 4 years of training of those neurosurgeons, right? 4 to 7 years. Right? For this robotic system, because many of those neurosurgeons, they are very familiar with this video game. So only take them around an hour to train with this robotic system. And then they are, become experienced. They can operate this robotic system. It's very intuitive, right? Then I want to quote our collaborator, Dr. Aman Patel. With his help, they means his trainees didn't need my thousands of hours of surgical expertise to approach my level of skill. Right? So imagine the potential impact if you can use this kind of robotic system, train many neurosurgeons in shorter time, and then deploy this robotic system all across the country. Really save stroke patients within the golden hour. Not only that, if you look at the performance, right, in terms of performance, one most important factor is the number of undesired steering maneuver. Right? So, for example, this guide wire touching the aneurysm, touching blood vessel, that's undesirable. Right? You may even pierce a hole on the blood vessel. So you want to avoid those. Right? For manual operation, many of those undesired steering are unavoidable, intrinsically unavoidable, because you need to rotate this guided wire robot inside a narrow blood vessel. Right? However, for the robotic system, very quickly you can decrease this to 0 due to intrinsic different operation mode. Right? So complication rate for this kind of neural operation, right, can reach up to 10 to 20%, mainly due to undesired steering. Right? Imagine the potential impact if we can deploy widespread this kind of robotic system for stroke treatment. Then what is the next step? Right? What can be the future? Right? We believe we can harness modern technology such as AI to further relieve the cognitive burden of the neurosurgeon, to further automate this robotic system. So here is one example. Right? If you think about this problem, right, it's quite straightforward. Under high resolution medical imaging, right, you know the current location of your guide wire, you know the desired branch of the blood vessel. Then the problem is really what magnetic field I should apply to bend my guide wire to this desired branch. Right? That's an inverse problem. Again, it's a difficult mechanics problem, but with the current neural network, we can do millions of simulation based on the model, and then use this model to train this neural network so that the neural network can predict the control variable, apply the magnetic field, so that to bend this guide wire to the desired location. Right? And then you may say there can be mistakes. Then the neurosurgeon can play the role of intervention, stop the machine navigation, and then use a joystick manual operation of this robotic system. Right? So that's our vision. Then here is some preliminary results. You can see in this whole process, no human intervention anymore. So this is fully automated. You can see this is like a self-driving of Tesla. So you are navigating inside the blood vessel. This is a location that requires some navigation. Then the system will call the neural network calculation. Then navigate to the next location that requires navigation. Then you have another predicted applied magnetic field. You navigate around this. Then you go to here. So I would say this is possible, and this technology will develop in parallel as the translation of the mature joystick control technology, so that they will go hand in hand. I believe that's the process of making impact with this kind of technology. So this is our philosophy. Soft robotics plus modern technology such as AI can give us a future precision medicine, especially in the sector of endovascular treatment and this endovascular navigation and treatment. Right? So scientists, we are on board because we are doing science for curiosity and also for societal impact. Surgeons, they are on board, right? Because they know they cannot be fully replaced by robots. It's impossible. Lots of work requires their attention. However, they can be empowered by software robotics and AI. They can save more lives safer, faster, remotely, with much less training time. Right? Patients, time lost equal to brain loss. Right? You can see very rarely all stakeholders are on board, and the other technologies such as imaging, robotics, control are all converging towards this extremely important societal challenge. So I believe we will move this forward with the effort from different sectors of the society. Eventually, the goal is to treat stroke patients within this golden hour.